Today, we're diving into an idea that allows neural networks to become, as this foundational paper puts it, outrageously large neural networks. It's how we can scale models to hundreds of billions or even trillions of parameters.
That sounds like a recipe for exploding compute costs. We just learned about transformers, case number TCM 123001, and they already push the limits. How can models get even larger without becoming impossible to train or run?
That's exactly the problem this paper tackles. It starts by stating a fundamental truth. The capacity of a neural network to absorb information is limited by its number of parameters. More parameters generally mean more knowledge can be stored.
So to get more capacity, we need more parameters. But if we just make every layer wider or deeper, computation just scales up proportionally, right? We hit a wall pretty quickly with that approach.
This paper introduces a different paradigm, conditional computation, where parts of the network are active on a per-example basis. Instead of everything running all the time, only relevant parts activate.
Okay, so it's like having a huge library, but you only ever open the books relevant to the question at hand. You don't read the whole library every time.
Exactly. This allows dramatically increasing model capacity without a proportional increase in computation. Think of it like a specialized consulting firm. Instead of one generalist trying to solve every problem, you have many experts.
So for each new client, the firm directs them to just the right few experts who can solve their specific problem. That's a good analogy. It uses a lot of potential knowledge without having every expert work on every case.
The core innovation here is the sparsely-gated mixture of experts layer, MOE. It's a special kind of layer in the neural network that implements this conditional computation.
Sparsely gated. So the gating part determines which experts get activated, and sparsely implies only a few at a time. This is getting interesting.
Precisely. The MOE layer consists of up to thousands of feed-forward subnetworks. These are the experts in our analogy, specialized for different kinds of inputs.
So a single layer can now contain thousands of these smaller networks. That's where the massive increase in potential capacity comes from, right?
And the key is how they're selected. A trainable gating network determines a sparse combination of these experts to use for each example. It learns to route the input data.
A trainable network decides the routing? That's powerful. It's not hand-designed rules. The model learns which expert is best for which input data, almost like a traffic controller.
This mechanism led to greater than 1000x improvements in model capacity. Now, let's look at how this core idea translates into the modern transformer architecture we're familiar with.
So the big picture is clear. Vast capacity through conditional computation. Now, I'm curious about the specific building blocks and how this gating actually works inside a transformer.
This Hugging Face blog post, Mixture of Experts Explained, provides an excellent overview. Let's ground our understanding of what an MOE actually is in the context of transformers.
So we're replacing something in the standard transformer architecture with an MOE. Which part is it, and why there specifically?
In a transformer, which we covered in case SHTCM15002, the sparse MOE layers are used instead of dense feed-forward network FFN layers. Remember, FFNs typically process each token independently.
The FFN is a standard component in each transformer block. So instead of one big FFN, we get an MOE layer there. That makes sense for where to plug in the experts.
Yes, within that MOE layer, there are several experts, where each expert is a neural network. They're typically smaller FFNs, each specializing in processing certain types of information or input tokens.
It's like instead of one large general-purpose processor in the FFN, we have a bank of smaller, specialized processors, each one good at a particular kind of computation or data pattern.
Then, we have a gate network or router that determines which tokens are sent to which expert. This router is another neural network that learns the best pathway for each incoming token.
So every token that enters the MOE layer first goes through this router, which then decides, you token, go to expert A and expert C, or something similar?
Precisely. And importantly, we can send a token to more than one expert. It's not always just one, which adds flexibility. The router output often includes weights for combining the expert outputs.
Wait, so it's not just a binary choice. The router isn't just a switch. It's more like a mixer that blends the outputs from a few chosen experts? That's a crucial detail.
Yes, exactly. And the big benefit? MOEs are pre-trained much faster versus dense models. You get high quality for less compute or higher quality for the same compute.
That's a huge claim. It sounds like a cheat code for training large language models. Where's the catch? Does this mean we don't need giant clusters of GPUs anymore?
There's a trade-off. While computation is sparse, MOEs require high VRAM as all experts are loaded in memory. Even if only a few experts are active, their parameters still need to reside on the GPU.
Ah, so you're not saving memory, just computation. It's like having all the specialized consultants on staff. Even if you only use a couple for any given client, they still need offices.
That's a great way to put it. Now that we have the high-level intuition, let's dive into the specifics of how this gating actually functions and the mechanisms that make it work reliably.
I'm ready. How does this trainable gating network make its decisions? And how do we ensure it doesn't just send everything to the same expert?
We've established that sparsity uses the idea of conditional computation. The router's job is to enforce this sparsity, ensuring only a subset of experts are active for each token.
So the sparse part is about making sure not all experts are used. It's not just having a lot of experts, it's efficiently choosing among them.
This section explains a learned gating network, G, decides which experts, E, to send a part of the input. The input token is fed into the gating network first.
So the gating network takes the token representation, processes it, and outputs scores for each expert. What does it typically use to make that decision?
The original paper introduced noisy top K gating. Instead of a simple softmax, it adds tunable noise to the expert scores, then selects the top K experts.
Adding noise seems counterintuitive. Is it to prevent the gating network from becoming too rigid, always picking the same few experts? To encourage exploration?
That's exactly right. After adding noise, the router's primary job is to only pick the top K experts. This ensures sparsity and limits computation.
So K is a hyperparameter reset. If K equals 2, then only 2 experts process each token, regardless of how many total experts there are in the layer.
This blog post asks, why not just select the top expert? The initial thinking was that routing to more than one expert was needed for the gate to learn properly.
So if K equals 1, the router might get stuck or not generalize well. It needs a bit of a soft decision to learn the right routing. That makes sense for training stability.
A crucial problem in MOEs is load balancing tokens for MOEs. Without it, some experts become overused hotspots, while others remain underutilized.
like a few popular consultants getting all the clients, while others sit idle. That would defeat the purpose of having many experts if only a few are actually doing work.
To combat this, an auxiliary loss is added to encourage giving all experts equal importance. This loss term is incorporated during training to distribute tokens more evenly.
So the router isn't just learning to pick the best experts, but also learning to pick experts in a way that keeps everyone busy. It's balancing performance with utilization.
Precisely. This combination of sparse gating and load balancing makes the MOE layer practical. Now, let's see this in action with a concrete example, the Mixtral model.
We've seen the theory and the challenges. I'm excited to see how this translates into a state-of-the-art model that's actually performing better in the real world.
Mistral AI recently released Mixtral 8x7B, a high-quality sparse mixture of experts model. This is a powerful demonstration of MOE in a cutting-edge large language model.
So this isn't just academic. MOE is driving some of the best open source models available right now. This makes the whole mechanism feel very relevant.
Mixtral is a decoder-only model where the feed-forward block picks from a set of 8 distinct groups of parameters. This directly implements our MOE layer in the FFN part of the transformer decoder.
So 8 experts are available in each MOE layer, and for every token, the router selects a subset from these 8 to do the actual computation?
Exactly. Specifically, a router network chooses 2 of these groups, the experts, to process the token and combine their output additively. So K equals 2 in this specific implementation.
That's the sparse part of sparsely-gated in action. Only 2 experts out of 8 are active per token. That drastically cuts down computation compared to a dense model of equivalent total size.
This is the most compelling result. Mixtral has 46.7B total parameters, but only uses 12.9B parameters per token. This is where the magic happens in terms of efficiency.
Wow, that's a massive difference. It means the model has the potential capacity of 46.7 billion parameters, but the actual computation for any given token is only like a 12.9 billion parameter model.
Yes, it processes input and generates output at the same speed and for the same cost as a 12.9B model. This is like having a huge team of specialists, but only paying for the few you need at any moment.
So you get the benefit of a much larger, more knowledgeable model without the proportional increase in inference costs. That completely changes the cost-performance trade-off.
And the results speak for themselves. Mixtral outperforms Llama 2 70B on most benchmarks with 6x faster inference. This isn't a small gain, it's a significant leap in efficiency.
6 times faster for better performance? That's what makes it a high-quality sparse mixture of experts model. This is a real game changer for deploying powerful models.
But remember our earlier point about VRAM. The Hugging Face article reminded us that even for Mixtral, you need high VRAM to hold a dense 47B parameter model. All those parameters need to live in memory.
Right, so while computation is sparse, the model footprint is still large. It means you need powerful GPUs, but you're getting more bang for your compute buck once it's loaded.
Precisely. Mixtral shows how the MOE architecture delivers both state-of-the-art performance and remarkable efficiency, fundamentally altering how we approach large model design. It's a prime example of where conditional computation shines.
This has been incredibly clarifying. I am Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.